Given the function g of x equals x squared ln of x, find all intercepts, critical numbers, intervals where the function is increasing and decreasing, local maximum and minimum values, inflection points, and intervals where the function is concave upward and concave downward. Then use that information to sketch a graph of the function. The first thing I want to note is because there's an ln of x here, the domain goes from 0 to infinity. So we don't have to worry about negative numbers. And then we have some intercepts to look at. We are not going to have any y-intercepts because our function is not defined at x equals 0. But we might have some x-intercepts, or at least one. If we set our function equal to 0, x squared ln of x equals 0 when either x squared equals 0 or ln of x equals 0. X squared equals 0 happens when x equals 0, but again, that's not a part of our domain, so we can throw that out. And then ln of x equals 0, specifically when x equals 1, because ln of 1 is equal to 0. So this is going to be an x-intercept. So we've got an x-intercept at 1. Then for critical numbers and the intervals where the function is increasing and decreasing, we're going to need to differentiate. The derivative here is going to come from the product rule. We've got the derivative of the first, which is 2x times the second, ln of x, plus the first, x squared, times the derivative of the second. The derivative of ln of x is 1 over x. And so this ends up becoming 2x ln of x plus x. And if we want, we can factor out an x. So x times 2 ln of x plus 1. And the only place this is undefined is where the original function is already undefined. So we don't have to worry about critical numbers arising from the derivative being undefined, but the derivative could equal 0. And that could happen when x equals 0. But again, that's not part of the domain, so we ignore that, and we focus on the second factor equaling 0. So we need 2 ln of x plus 1 to equal 0. If we subtract 1 and divide by 2, that's going to be ln of x equals negative 1/2. And if we rewrite this in exponential form, that's going to be e to the negative 1/2 power equals x. And this is approximately equal to 0.61. So that is going to end up being a critical number. And so we are going to need to make a sign chart with e to the negative 1/2 as our critical number. Also, we'll put 0 there because the function's not defined to the left of 0. And so our factors are x, which is always positive to the right of 0, and then 2 ln of x plus 1. And goodness, we might not know where that is positive or where that is negative, so we could pick values in each interval to plug in and evaluate this to see if it's positive or negative. And in the end, we end up with negative and then positive. I will leave that as an exercise for you to pick an x value in each of those intervals and plug it in. And then in the end, our derivative is going to end up being negative and then positive, which means decreasing and then increasing. And that's going to give us a local minimum at e to the negative 1/2. If we plug that in to find the function value, g of e to the negative 1/2 is going to be, well, if we square that, that's going to be e to the negative first, because squaring 1/2 ends up being 1. And then ln of e to the negative 1/2 is just going to be negative 1/2. So it's going to be negative 1/2 e to the negative 1, or negative 1 over 2e. which is approximately equal to negative 0.18. So our local minimum is going to be at approximately 0.61, comma, negative 0.18, if we're going to want to graph that. Then we want to deal with concavity, which means we're going to have to take the second derivative. So we're going to have to differentiate the first derivative, and I'm going to pick this version to differentiate because it seems to be the nicest version. So our first derivative is 2x ln of x plus x. And then if we differentiate that, again, we're going to use the product rule here. And so we've got the derivative of the first, which is 2 times the second ln of x, plus the first 2x times the derivative of the second, 1 over x, plus that derivative of x is 1. We know the x's here are going to cancel, so this is going to be 2 times 1 is 2, plus 1 is 3. So this is going to be 2 ln of x plus 3. And if we want to check the concavity to find any possible points of inflection, we need to know when this equals 0. So if we subtract 3 and divide by 2, this will happen when ln of x is negative 3 over 2. And if we rewrite this in exponential form, that's e to the negative 3/2 equals x. And that occurs at approximately 0.22. All right, so we are going to need a sign chart to figure out when this is positive and negative. Again, the domain starts at 0, and then we've got our e to the negative 3/2 at 0.22. And let's see, what is our factor? 2 ln of x plus 3. And if we plug in values in those ranges, we're going to end up with negative and then positive. So it's going to be concave down and then concave up. And so we've got a point of inflection at 0.22, comma, and then we've got to plug that into the original function to figure out what the y value is. I am just going to use a calculator because that makes life easier. And I get approximately negative 0.07. Very, very, very tiny. Now let's see what we've got. Now I am running out of space here, so I've got to have this overlap with some of the text, but life will go on. So let's see what we actually have. We have an x-intercept at 1, so we know we can plot a point at 1, 0. We have a minimum value at 0.61, negative 0.18. Now, if this is 1, then each one of these is 0.25. So 0.61, negative 0.18 is going to be around here. That's going to be our minimum. We have a point of inflection at 0.22, negative 0.07. That's going to be right around here. And our function is doing what? It's decreasing until the minimum, and then it's increasing. And we said it's going to be concave down until that point of inflection, and then concave up everywhere else. So it looks like if we start with our minimum and we go to the right, we're going to be increasing and concave up. So probably something like that. And then in these areas, we are decreasing and we are concave down and then concave up. But we're not decreasing very rapidly. So that's going to be concave up a little bit. And then this is going to be concave down. If we had all the time in the world, we could find the limit as x approaches 0. because we want to know where this function ends. We don't have time or space for that, but if you do that, you do end up with 0. But the function is not defined at 0, so we've got an open circle there. And so we start at the origin, and then we decrease downward with concavity down, and then concavity upward, and then we start increasing again like that. So it's maybe not the most interesting function if we just glance at it, but there's a little bit going on down here that you would only see with calculus. A table of values is not going to give us the intricacy that's happening in this area down here.